Welcome to Online Precalculus. Today, we're going to cover section P3, Radicals and Rational Exponents. So in this section, our objectives are to evaluate square roots, simplify expressions of the form square root of a squared, we'll use the product property to simplify, quotient rule to simplify, add and subtract square roots, rationalize denominators, evaluate and perform operations with higher roots, and finally, understand and use rational exponents. So we start this section with talking about square roots. And previously, from our work with exponents, we know that the square of 5 and negative 5 is 25. So we can see that 5 squared is 25, as well as negative 5 squared, because it's in parentheses. So negative 5 squared is also 25. So when we do the reverse of that, that's called finding the square root of a number. So if we reverse that thinking, we can say that one square root of 25 is 5, and another square root of 25 is negative 5. So in general, if b squared equals a, then b is the square root of a. Okay? But you should know that when you press the button for square root on a calculator, or when you're talking about generally a square root, we tend to use that symbol right there, and that symbol is used to denote the non-negative or principal square root of a number. So when you see the square root of 25, we're talking about only 5, because that symbol, the square root symbol, denotes the principal square root of the number. Even though 25 has 2 square roots, by using the symbol, we are talking about only the positive one. Okay, so the symbol, radical symbol, that we use to denote the principal square root is called the radical sign. And the number under the radical sign is called the radicand. And together, when we put all this together, it's called a radical expression. Okay, and here's the definition of a principal square root. What we just talked about, non-negative real number. And that's important. If we're talking about a square root, then a, the part underneath the square root, the radicand, has to be non-negative. Okay, because if it was negative, then it would be imaginary. We also don't say just positive, because underneath the radical can be a 0. So we usually use the term non-negative for that, because it is possible for that to be 0. Okay, so if a is a non-negative real number, the non-negative number b, such that b squared is equal to a, is denoted as b is equal to the square root of a, and that is the principal square root. If I wanted the opposite, if I wanted the negative square root, I would use the symbol of a radical sign with a negative in front of it. Okay, so therefore, the negative square root of 25 becomes negative 5. And then that kind of makes a lot of sense, because if you're saying that the square root sign denotes a non-negative number, if we put a negative sign in front, that means we're going to take a non-negative number and make it negative. Okay? So the way we are going to differentiate between positive and negative square roots when we're using the square root symbol, when we're using the radical sign, is just with a negative sign in the front. Okay? So let's calculate some square roots. And these should be fairly simple. So square root of 64, we're asking what times what is equal to 64. And that is going to be equal to 8. And not negative 8, not plus or minus 8, just 8. As opposed to b, which would be negative 7, because there is a negative in the front of that. Okay? Fractions, right? 2 ways to think about this. We could just say what times what gives me 1/4, or I could even take the square root of the top and the square root of the bottom to give me 1/2. Okay? The square root bar acts like parentheses, so we should do everything underneath the radical sign first. So this would be the square root of 25, which would be 5. different than part E, which we now would do the two separately. And we get a very different result here because square root of 9 is 3, square root of 16 is 4, and we would get 7. So depending on whether or not we have both things underneath a radical or two separate radicals, will change your order of operations. Okay? Let's try our checkpoints. All right, so same general idea. So part A, the square root of 81 is 9. Part B, the square root of negative 9 is negative 3. For part C, 1 over 25, that turns into 1/5. Part D, oops, we would start by adding those two together to give me the square root of 100, which would be 10, as opposed to part E, which would be the square root of 36 is 6, plus the square root of 64 is 8, and then 6 plus 8 is 14. So definitely two different numbers there when we use a different order of operations. Okay. A number that's a square of a rational number is called a perfect squared. All these were perfect squares because they all worked out to uh, perfect numbers, right? No decimals. Okay, they all worked out to either integers, or they all worked out to rational numbers. All the radicands in the previous chair are all perfect squares, and let's see what happens when the radical expression of the square root of x if x is a negative number. Is the square root of a negative number a real number? For example, consider the square root of negative 25. That is not real. The square root of a negative number is not real. It doesn't work. There are no two numbers that you can multiply together, two of the same numbers, to give you a negative 25. Okay? So if a is a non-negative number bigger than 1, then a squared is equal to a. The square root of a squared is usually equal to a. So that's true for all this, right? The square root of 3 and then square that is going to be 3, and so on and so on. So let's start to simplify expressions in the form of the square root of a squared. I'm missing my top here. Okay. So you may think that the square root of a squared is always equal to a, but that's not always true if you look at these next two examples, right? The square root of a positive 4 squared is equal to 4. However, the square root of a negative 4 squared is also equal to 4, not negative 4. Negatives don't come out of square roots because they because there's no number inside that you can multiply twice that would give you a negative number. Okay, so what this means is you can see that if you are taking the square root of a squared, it's the principal root, the positive root, is always going to be equal to the absolute value of a. And while it's easy to see with numbers, this can have a big difference on simplifying expressions with variables in the expression, and that could get a little tricky. However, we're not going to touch on that too much in this section, but we are going to use some of the properties to help simplify square roots. So a rule for multiplying square roots can be generalized by comparing the square root of 100, right? 25 times 4, and the square root of 25 times 4. So if we think of the square root of 25 times the square root of 4 is 5 times 2 is 10, whereas if we multiply them together first, we also get 10. And this leads us to the product rule for square roots. And it says that if a and b are non-negative real numbers. So what this is saying is that the stuff underneath the radical, if we are going to use the product rule, the stuff underneath the radical sign must be two positive numbers, or 0, so two non-negative numbers. So what that will really do is it will eliminate this situation right here, where we need to worry about an absolute value sign. because we're starting with two positive numbers. We're not starting with a negative number, okay? So that makes these problems a little bit simpler, and it means that we don't have to think about something called the even odd rule, where you would have to include absolute value signs on your answer if you took the even root of an even exponent and got an odd exponent answer in your solution. This is also with variables we're talking about here. But by using the product rule and by realizing that the two things inside of the radical must be positive, must be non-negative, then we don't need to worry about that at all. And we can pull two radicals apart or put them both together with the goal of simplifying it. And a square root is simplified when its radicand has no factors other than 1 that are perfect squares. Like the square root of 500 is not simplified because it has a factor of 100. That's a perfect square. Okay, so the goal is to factor those out. And that's exactly what we're going to do with my first problem here. So the way that I simplify the square root of 500 is I separate it into the largest perfect square factor that I can think of that goes into 500. So that would be the square root of 100 times 5. Square root of 100 is 10. The square root of 5 cannot be simplified anymore, and that is my simplified expression, simplified square root. Now, this is what I was talking about before with a variable, right? Because of the fact that we are multiplying these two things together, and I can pretty much turn this into 6x times 3x, which would be the square root of 18x squared. So now I need everything that's a perfect square. So what I can do is I can separate this into 9x squared times the square root of 2. Well, the square root of 9 is 3, the square root of x squared is x, and the square root of 2 sort of gets left behind. Good rule to sort of follow here is to write things that are not part of the square root in the front, and that just prevents something like this, where you're not really sure if the x is inside or outside of the square root. You could go like that, but that looks a little bit weird. Typically, we just put the x and any constant in the front. Okay, now, what I was talking about before is that because we use the product rule, because we put these two radicals together, because there's two things multiplied together, I have to assume that both of these numbers are positive, and therefore I don't need to put an absolute value sign around the x. And we can just leave it like that. That would not be true if the question didn't involve a product, and then you would need the absolute value signs. But that again is something that we can talk about in a different section. All right, so let's try two more. One with a number again. So the square root of 75, I have to ask myself, what is the biggest perfect square factor that goes into 75? And I can separate that into the square root of 25 times the square root of 5, times the square root of 3, 25 times 3, 75. And so that would give me 5 square root 3. For the second one, the first step is to put them together. So that gives me 50x squared. The biggest perfect square that goes into 50 is 25 and times 2. Square root of 25x squared is 5x. The square root of 2 gets left behind and cannot be simplified anymore. When simplifying square roots, what happens if I use a perfect square factor that isn't the greatest perfect square factor? Well, that's a great question. The answer is you just made the question a little bit harder for you. So for instance, take a look at the two examples. Okay, so what we did for the square root of 500 was 100 times 5, so that's radical 10 times 5. If we didn't see that and we broke it down into 25 times 20, we'd be left here, 5 radical 20. But the problem is that 20 has another perfect square factor, and it's 4. So then I would break that up into 4 times 5, and the square root of 4, which is 2, times the 5 that was already outside gives me my same answer of 10 square root 5. The problem here, and it says it in bold, is this is more work if you don't see the greatest perfect square factor. Okay? But as long as you in the end get to the answer, that's good. Okay? So another property for square roots involves division, and it's called the quotient rule. Again, A and B are going to be non-negative real numbers, which means we don't need any absolute value signs or anything weird like that. And it basically says that we can take a fraction and we can split it into 2 square roots, or we can take 2 square roots and put them together underneath one fraction, depending on what we want to do. So let's take a look at some problems. In the first one, the easiest, 100 is not divisible by 9. If it was, I would divide it and then take the square root. I would use sort of the same idea as I did before as the square root as parentheses. But since that doesn't work, I can separate it into 2 different parts and then get 10 over 3 as my solution. As opposed to the next part, which I would put both of these together in order to simplify them. Okay, so 48 over 6 simplifies into 8, and x to the third over x simplifies into x squared. Now I can take that from there and I can separate this into 4x squared times the square root of 2. And 4x squared is a perfect square, gives me 2x square root 2. And again, I don't need any absolute value signs in this expression because the first thing I did was use the product rule, or sorry, the quotient rule, which means that everything has to be a positive number. Okay. 2 more problems again. So for part A, I can break it up. Square root of 25 over square root of 16 just gives me 5 over 4. And for part B, I want to put them together first in order to reduce the fraction and to cancel some things out, which gives me 150 divided by 2 is 75 x squared. And we've done 75 previously. It's 25 times 3. That's 5x square root 3. Right? The 25x squared simplifies to 5x, and there's a radical 3 left behind. Okay, so adding and subtracting square roots. So 2 or more square roots can be combined using the distributive property provided they have the same radicand. The stuff underneath the radical is exactly the same. These are called like radicals. Like radicals. And just like we were adding something with like terms, right? The way we do that is we factor out the x and then we can combine the 7 and the 6. We really don't need to write that middle step. We can just realize that they are like radicals and they add together. And because we're factoring out the square root of 11, nothing happens to it. Okay, it doesn't turn into the square root of 22. We're not adding anything. We're not multiplying them together. And we can just add the 2 radicals together, provided that the radicals are alike. Okay, so for this case, all right, we just have 7 and we have a 5. So that gives me 12 square root 2 when I put them together. You don't see anything in the front. You can assume that it is a 1. So this gives me negative 6 square root 5x. As long as these 2 are exactly the same, I can combine the 2 radicals. Okay. Again, 8 and 9 give me 17. The square root stays the same. And if you don't see anything in the front, just like any other variable, it represents a 1, which makes this negative 19 square root 17x. In some cases, radicals can be combined once they have been simplified, which means that if a radical looks like it is not alike, like these two, they are not like radicals, but maybe you can make them like radicals if you simplify them first, which is the case with this example, right? You can change the square root of 8 into 2 radical 2 and then combine them to 3 radical 2. So just looking at part A, I know that I can maybe do something if they were the same. So this is 7 radical 3, nothing I'm going to do about there. Oh, but the square root of 12 is the square root of 4 times the square root of 3, which means that square root of 4 turns into a 2, and we get 9 radical 3, 9 square root 3. Okay. For the second one, okay, we got some x's, we got some bigger numbers here. Okay, still not too bad. So we have the 4 outside, it stays there. I'm going to change this to a 25, and 2x gets left behind. 25 is 5 times the 4, which is outside already, gives me 20 square root 2x. Second part, minus 6 times 32 is 16 times the square root of 2x. The square root of 16 is 4, and 4 times 6 is 24. So it's minus 24 square root of 2x. The 2x's are alike, so we turn this into negative 4 square root of 2x. Let's try 2 more, okay? Our checkpoint problems, okay? So the square root of 27 simplifies into 9 times 3. So this would be 5 times 3 radical 3 to give me 15 radical 3 plus the square root of 12, which we just did from above, is a 2 radical 3, which gives me 17 radical 3. Part B. So we have the square root of 18 is 9 times 2. So that's 6 times 3 radical 2x, which gives me 18 radical 2x. Let's do the second part. Square root of 8 is 2 radical 2. So that's 4 times 2 radical 2x. And 8 2x. The 2x's are the same. So this gives me 10 square root 2x. All right, so one thing we need to realize about radicals is we don't really like to leave square roots and radicals in the denominator. So if we were to use a calculator to calculate both of these things, I didn't bring a copy of that, but I'll leave that up to you. If you actually put both of those in a calculator, you're gonna get the same, the same irrational number. It doesn't stop, so same approximation. This is not something abnormal because they are both the same fraction, just written in a different way. And you can see that if you write 1 is the multiplicative identity, so if you multiply or divide anything by 1, it does not change its value. So as long as I have the same thing over the same thing in the top and the bottom, right, you are multiplying by 1. So I can change my original fraction to be something that does not have a radical in the denominator. When you do this process, when you change a radical expression into something that doesn't have a radical in the denominator, this is called rationalizing the denominator. And if the denominator consists of the square root of a natural number that's not a perfect square, the easiest way to rationalize it is to just multiply the numerator and the denominator by the smallest number that produces a perfect square, right? So it is easy to just say, okay, I have a square root of 6 in the bottom. I'm going to multiply the top and the bottom by a square root of 6 to give me 15 square root 6 over the square root of 36, which is 15 square root 6 over 6. Okay. Now, from here, you could simplify, right? 15 over 6 can reduce to 5 over 2. And that would be my final answer. Now, the difference with part B is you shouldn't just multiply the top and the bottom by the square root of 8. That will work, right? It'll make the denominator not a radical anymore, but there's an easier way to do it. Just multiply by the number, the smallest number that produces a perfect square in the denominator. By doing it this way, there's less to cancel at the end. Square root of 16. Don't cancel anything yet. You don't cancel anything until we are done with the problem. So that's 12 square root of, 12 square root 2 over 4. And then 12 over 4 gives me my 3 square root 2. Okay? Let's try 2 more. So for part A, the best way to do it is to just multiply the top and the bottom by the square root of 3 to give me 5 square root 3 over square root of 9, which is 3. Can't cancel those two, right? Those are, one's a radical 3, one's a normal 3, so they are not the same thing. So don't be tempted to cancel something underneath a radical with something that's not in a radical. Part B, however, I know that you would be tempted to multiply 12 by the square root of 12 by the square root of 12, but easier if we multiply the top and the bottom by the square root of 3. It's going to be 6 square root 3 over the square root of 36. So that's 6 square root 3 over 6. Now I can cancel those two to give me the square root of 3. Okay, so try to look for the square root, the smallest square root that you can multiply. Sometimes, if you have a sum or a difference of two terms that are radicals, in order to make one or go away, we're going to have to use something called conjugates. Okay? So conjugates occur when we just have the same terms, only one's a plus in between, one is a minus in between. And a funny thing happens when we multiply two conjugates together, and you can see by distributing the radical a to both of those and the b to both of those, we can see what happens is we get the square root of a squared. We have a negative ab, a positive ab, and the square root of b squared. Okay, these two cancel out because they are opposites of each other. And when you square a radical, the radical goes away. So that means when we multiply two conjugates together, we're always going to get a minus b, which happens to be something without a radical. Okay, so how do you rationalize a denominator that contains two terms with more than one square root or one or more? You multiply the numerator and the denominator by the conjugate of the denominator. So the conjugate for the first fraction right there is, you can see 5 minus radical 3. Same first number, opposite second number. Same first number, opposite second number. Same first term, opposite second term. We'll deal with this a lot later, something that occurs in calculus. So the product of the denominator and conjugate is found using the formula. We just talked about that. And again, it does not contain a radical, which is what we want. So to rationalize this, we are going to take this expression and we're going to multiply the numerator and the denominator by the conjugate of the denominator. And the shortcut for multiplying the conjugate of the denominator is going to be a squared minus b squared. Okay? That will always work. That is the formula, and we can see that will always happen when we multiply two conjugates together. We're always going to get a minus b, right? So it's going to be the square root of a squared minus the square root of b squared. Okay. Oops, wrong way. Here we go, back here. So again, we would have to square this because it's not a square root, square this, and then we're going to subtract those two terms. Here, I'm going to have to distribute. So we get a 35 minus 7 radical 3, 7 square root 3. And now it's just a matter of simplifying the two terms. So we have 35 minus 7 square root 3 over 22. Nothing there that I can cancel, nothing that can reduce, so that is simplified. Let's try it again. 8 over 4 plus the square root of 5. So to get rid of the radical in the denominator, I'm going to multiply by the conjugate of the denominator. And again, if you wanted to, distribute this out, FOIL it together, you would see that all the middle terms cancel, and we get 16. We can just do this: 16 minus 4 radical 5 plus 4 radical 5, right? Those two terms cancel out, minus radical 25, which is 5. Distribute the numerator. We have 8 times 4 is 32 minus 8 square root 5. So that is 32 minus 8 square root 5 over 11. And that happens to be simplified. So for most of this section so far, we've been talking about square roots. There are other kinds of roots, okay? So we can define the principal nth root of a number symbolized with a little number right there called the index as follows, okay? So the nth square root of a equals b means that b to some power n equals a. So in a square root, that means b squared is equal to a. If it was a 3 up top there, that would symbolize a cube root, which means that b to the third power is equal to a. Okay? So if n, the index, is even, then a has to be non-negative. Okay? And if it is odd, it can be any real numbers, because you are allowed to take the odd root of negative numbers, because a negative times a negative times a negative is a negative. So the cube root of 64 is 4, because 4 to the third is 64. And the fifth root of negative 32 is negative 2. Right? And it's the same vocabulary that we learned applies to these nth roots. The symbol is called the radical symbol, and the expression is called the radicand. Okay? And a number that is the nth power of a rational number is called a perfect nth power, perfect square, right? Also leads to perfect nth power. 8 is a perfect third power or perfect cube, because 2 times 2 times 2 is 8. So in general, one of the following rules can be used to find the nth root of a perfect nth power. So if it's odd, if n is odd, the nth root of a to the n is just whatever's underneath. And if it's even, right, negatives cannot come out of even roots, so it is always going to be positive, just like square roots. So that's like fourth roots in this example right here, right? The fourth root of negative 2 to the fourth power, right? We would do the fourth power first, and it would become positive, so it would become the absolute value of negative 2 as my answer. The product rule and the quotient rule work the same. As long as you have the same index, you can use the product rule, either pulling two radicals apart or putting them together, or the quotient rule, either putting them together into one fraction or pulling them apart. Okay? So that means to simplify these higher level roots, we have to start to think about numbers that are perfect third powers, perfect fourth powers, perfect fifth powers, okay? And we have to see a way to simplify these things using those numbers. So for part A, I want to think about the biggest number, the biggest perfect cube that goes into 24. And the way I can start to do that is I can say, okay, well, 2 to the third is 8. Okay, 3 to the third is 27. That's already too big. So what's the biggest perfect cube that goes into 24? It's 8. Okay, happens to be 8 times 3. Okay, cube root of 8 is 2. So it's 2 cube root 3. Make sure you don't lose the index. Make sure you keep that little 3. The textbook does it nicer, keeps it right in the little nook of the square root symbol right there. Okay. Again, part B, now we're taking fourth powers. So 2 to the fourth power is, well, before we get there, hold on. Before we get there, let's put these two together, and we get that 8 times 4 is 32. So now I need to find the biggest fourth power that goes into 32. Well, 2 to the fourth is 16. 3 to the fourth is 81. 81 is too big, but hey, 16 goes into 32. So now I can separate that, and neither one of these were perfect fourth powers. Okay, these don't cancel, they don't reduce. It's not 1. So I couldn't do anything with the start of this, but once I put them together, I can split this into 16 times 2, and the fourth root of 16 is 2 fourth root 2. Part C, again, I could, if it simplified, try to divide these first, but nothing can happen. So I just look at the fourth root of 81 over the fourth root of 16. Fourth root of 81 we saw up there was 3, and 16 was 2. To simplify this into a nice fraction. Let's try our checkpoint problems. So the third root of 40, again, if we look at my perfect cubes, right, 2 to the third is 8, 3 to the third is 27, 4 to the third is 64, right? So 64 is already too big. 27 doesn't go into 40. Luckily, 8 does. So 40, 8 times 5. So we split this into 8 times 5. And so I would get 2 cube root of 5. Fifth roots. Fifth root of 8, nothing multiplies together 5 times to get 8. So I'm going to put these together, and I get the fifth root of 64. And luckily, that is no, sorry, it's not. It's not a perfect fifth root. If I'm not sure, I can go through my chart again. 2 to the fifth power is 32. That goes into 64. 3 to the fifth power is 243. Yeah. Okay. So 243, way too big, but 32 goes into 64. So that's the fifth root of 32 times the fifth root of, and I could write them together or separately, it really doesn't matter, times 2. The fifth root of 32 is 2 fifth root of 2 left over. And again, the easiest way to do part C is to split it. 125 over the third root of 27. Cube root of 125 is 5. 5 times 5 times 5 is 125 over 3 times 3 times 3 is 27. Okay, so we can use the same properties that we did before with adding and subtracting. So adding and subtracting square roots often involved simplifying terms. The same idea applies for any higher level roots. If they're not like radicals, if they're not already the same, then I have to simplify them first. Okay, so when I look at this, I have to do whatever I can to simplify it. So this turns into 5 times cube root, let's change that to an 8 times 2. Cube root of 8 is 2. So that's 5 times 2 times the cube root of 2. And so that would be 10 cube root 2 minus, well, nothing to do there because this is already a cube root of 2, so minus 11 cube root 2. So my answer is negative 1 cube root 2. Okay. Let's try our checkpoint. So again, and here's a hint here. I'm probably going to make those the same. So it's probably going to have something to do with the radical 3, and it does. So 3 times 81 is 27 times the cube root of 3. The cube root of 27 is 3. And so that gives me 9 cube root 3 minus 4 cube root 3, because nothing happens with that one. And that just gives me 5 cube root 3. Okay, make a better root. Yeah, nice, pretty square root, or cube root, sorry. Okay. Next is this idea of a way to write radicals using exponents, okay? So we defined rational exponents so that their properties are the same as the properties for integer exponents. So we know that when exponents are multiplied with an exponential expression is raised to a power, right? So if we have 7 to the 1/2 power squared, power to a power, we multiply those exponents together, we would just get 7. That's true for the square root of 7 as well. So the square root of 7 squared also gives you 7. So both 7 to the 1/2 power and the square root of 7, if you square them, are both 7. So that also means that they're the same, they're a different way of writing the same number. Okay? And we can extend that with a formal definition. And so the definition of 1 over a to the n power means that if you have the nth root of a, you can rewrite it as a fraction, as long as n is bigger than 2. If it was a 1, it wouldn't do anything. As 1 over, or sorry, a to the 1 over n power is equal to the nth root of a. The denominator of the exponent is the index. Okay, and every property, not only the negative exponent property, but every property of simplifying, every property of exponents and how you simplify exponential expressions applies to fractional exponents. Okay? So that means when I look at the first one, when I look at part A, it is saying the 1/2 power, so that's the index. So it's a 2. So it means square root, which means this is 8. This is the index. The denominator of a fractional exponent is the index. So it's the cube root of 125, which is 5. And you can eliminate this step right here. If you just realize that 125 to the 1/3 power means take the cube root, you don't have to write it out. Remember my order of operations, and that is negative 4th root of 16, right? That negative stays on the outside because it is not in parentheses, unlike the next one, okay? So this becomes negative 2. Whereas, sorry, yes, it becomes negative 2. Whereas this one is the cube root of negative 27, which is negative 3. But here, the negative's on the outside of the square root, or the 4th root, and here it's on the inside of the cube root. Finally, remember that negative exponents mean fractions. So this means 1 over the cube root of 64. Okay? And the cube root of 64 is 4. So this is 1 over 4. Okay? So negatives on the base, do something to make it negative. Negatives in the exponent make it a fraction. Let's try those again. Again, very quickly here. Square root, so that's a 5. Cube root, that's a 2. Negative on the outside, fourth root, that would be negative 3. Negative on the inside, cube root, that's a negative 2. Whereas this turns into 1/3, a positive 1/3. A negative in the exponent makes a fraction. So in that previous example, each rational exponent had a numerator of 1. It doesn't always have to be 1. We still want to multiply exponents when raising power to a power. So you can see that a to the 2/3 is the same thing as a to the 1/3 squared. Okay, so that means that if we have a fractional exponent with a denominator of 3, that becomes the index of the radical, and the numerator 2 becomes an exponent in the radical. In either way, either on the outside or the inside. Doesn't matter which way we do it, because, of course, we could do the 1/3 power first, or we can do the squared first and then raise it to the 1/3 power. Either way, you're getting 2/3 when you put them together. Okay. So again, our formal definition here: if the nth root of a represents a real number and m over n is a positive rational number bigger than 2, greater than or equal to 2, then a to the m over n power is equal to the nth root of a to the m, or with the m underneath. Okay. And again, all of our properties of exponents hold. So if you have a negative exponent, it just means it goes to the bottom of a fraction. Now, if you are going to simplify an expression, if you are going to try to calculate a number, okay, I would suggest this method, okay, because unless it's not a perfect square, and then it doesn't really work out, you need a calculator to use it anyway, taking the root first and making the number smaller and then raising it to an exponent is easier than doing it the other way. We'll look at a problem in a minute. Okay, so the first form of the definition of a to the m over n shown below involves taking the root first. Again, this is preferable because it makes the number smaller. So do the root first and then do the exponent. So what does that mean? Here, okay, I could, if I wanted to, go 27 squared and get that I want to find the third root of 729. Well, I might not know that off the top of my head. So it's actually easier to do the third root of 27 and then square my answer, because I know the third root of 27 is 3 times 3 times 3. So it's 3. So 3 squared would give me 9. So that's what we're talking about here, is simplify or take the root first. So 9 to the 3 over 2, which would give me square root of 9 is 3 to the third power, so that's 27. Okay, square root of 9 simplifies to 3, then raise it to the third power. Negative exponents go to the bottom of a fraction and then they become positive. Fourth root of 81 is 3. So this is 1 over 3 to the third, 3 to the third again. Okay, much, much easier than trying to find the fourth root of 531,000, which is what 81 to the third power equals. Okay? So much, much easier to do these in your head if you make the number smaller by taking the root. So these three, cube root of 27 is 3, 3 to the fourth power, 81. Square root of 4 is 2, 2 to the third power is 8. Again, first step here is move it to the bottom of, move it to the bottom of a fraction. The fifth root of 32 is 2 squared is 4. Okay, so all the properties of exponents that we talked about in the last section can be applied to expressions containing rational exponents, which means we have to add exponents when they have the same base. We have to subtract them if we're dividing. We have to combine these exponents just the way we would if they were just numbers. For instance, in this expression, right? To simplify this, I have to get rid of all the fractions and I have to put all the x's together. So first, I'm going to put this 5 times the 7 together and give me a 35. Okay, now it becomes x to the 1/2 plus 3/4. Okay, and of course, make a common denominator, all that nice stuff, and we get that x is now to the 5/4. Okay, so make that a little nicer. You don't have to turn it to a radical. In fact, if the question started with fractional exponents, leave them as fractional exponents and just realize that if you have a fractional exponent in the denominator, you might have to rationalize it before you're done. Okay, let's try this one. So we start with 32 over 16, which is 2. And then we have two fractions, 5 over 3 and 3 over 4. Luckily, 5 over 3 is bigger than 3 over 4, right? 3 over 4 is a little bit less than 1, 0.75. 5 over 3 is bigger than 1. So I know my answer is going to wind up in the numerator, and then it's just a matter of, common denominator of 12 and subtracting the two fractions to give me 11 over 12. Okay. Now, again, if the fraction had wound up in the denominator, then we would have to complete this expression in order to simplify it. Let's try two more. This would be 10 x. They already have the same common denominator. That's nice. But when we put them together and get 12 over 3, you do have to reduce it. So definitely make sure that you reduce the fraction if you can, right? If you can. For part B, and that's all there is to part A. So for part B, we would get 20 divided by 5, which is 4. 4 is bigger than 3 over 2, which is nice, which means my fraction does not need to get rationalized, and we wind up with 5 over 2. 4 minus 1.5 is 2.5. Okay. Finally, the last thing we can do is rational exponents are sometimes useful for simplifying radicals by reducing the index. So when you look at this expression right here, you really can't simplify it at all because x to the third, really nothing can come out of a 9th root. But if you remember that the numerator becomes the power, the denominator becomes the index, it is possible to reduce this to the 3rd root of x. Okay. Again, for our checkpoint, the numerator is the exponent, the denominator is the index, which reduces to 1/2, and now I turn the 6th root of x to the 3rd into just the square root of x. And that is everything for section P.3, radicals and rational exponents.